In this video, we will talk about axial loading. So axial loads are applied in a structural member along the longitudinal or centroidal axis, like shown in this figure. And if this action of the load is increasing the length of the member, we talk about tensile loads, and tensile loads and the elongation due to these loads, they have positive signs. If this load tends to shorten the member, it is named as compressive loads. Compression and contraction have negative signs. So if you want to calculate an axial loading, what you do is very simple. You take the load divided by the cross-sectional area and you find the stress. If you are in the elastic region, we know that the Hooke's law is valid, so we can take this value, epsilon equals to sigma over E, and instead of sigma, you can put this value and you end up with this relationship. This, to define epsilon, we all know that the definition of strain is delta L over L. This is the elongation or shortening, and this is the length of the structural member. So here we have as an elongation delta. Delta divided by L is epsilon. So if you take out delta out of this equation, so you can write delta equals epsilon times L, and epsilon is given here, and at the end you have this relationship. So in axial loading, the formula we can use are for stress, for the strain, and for the elongation, these simple formulas. We can also consider the local effects of axial loading. So if you have a load acting on both ends, near the load, we see that the distribution of the stresses is not uniform. They are distorted. So, but Saint-Venant says that these localized effects due to the loads acting on the body, they dissipate or smooth out when you are sufficiently far away from the application of the loads. So near the loads, we have to consider the local effects, but if you are far away from the action of the loads, so these localized effects will smooth out. A simple problem. You see, we have a funny rod, 1, 2, 3 regions. In each region, the material is different. The cross-section is different. The length is also different. So the question is, find the most critical section. And the second is find the elongation of the bar. That means the total elongation of the bar. We know that we have to calculate the internal forces. For this, well, this is my loads acting on the rod. So in the regions, region 1, I make a cut and take the left side. The free body diagram shows me that the internal force must be 2P for equilibrium. When I cut in the second region, well, the internal force should be minus P for equilibrium. When I cut in region 3, well, the acting force is a positive 3P force. The internal force diagram, Well, you see 2p, 3p minus p. It seems that the maximum load is here, but we cannot say that the most critical section is region 3. Why? Because there, in each region we have different materials, different cross sections. So the stresses must be calculated one by one. Let's do this. This is my force diagram. Well, we have to calculate the factor of safety. What is the factor of safety? Well, I can take the yield strength of a material as the fail strength, fail stress, because when a material in a mechanical structure begins to deform permanently, we can directly assume that it is fails. We do not have to wait for rupture. Okay, so our yield stress is our fail stress. So the fail stress divided by the acting stress is my factor of safety. I have to do this calculation for each section. Start with region 1. Here we have an aluminum. The acting force is 2p. P was 10 kilonewton, so 2p is 20,000 newton. Section. So in this region, the acting stress is 100. In this region, the material is aluminum. Its yield strength is 300. So 300, the fail stress, divided by the acting stress, is the factor of safety. The same for region 2, bronze. Here I have a compression and a higher area. The acting stress is 25. The yield is 450. Well, here we have a very, very high, let's say, factor of safety. Next is region 3P, section 300. The material is steel. 600 divided by 300. The factor of safety is 2. In all regions, the factor of safety is higher than 1, so there will not be any failure. But you see, this is the region where the factor of safety is the highest. Let's start to calculate the elongation. So I have to calculate for each region the elongation. So we know this formula. I have to write it from region 1 to region 3. And so let's put the numerical value. Region 1, 20,000. Region 2 minus here plus. These are the length of the regions. These are the sections. And these are the elastic modulus of the sections. If you do these calculations, and at the end you have 1.589 millimeter elongation. Another problem. Well, we have a steel rod. Well, this is the blue one, rod. Its diameter is 20 millimeter. It passes through an aluminum tube with a cross section of 300 millimeters square. So when you look from the top, so this is your rod, this is the section, and this is the tube. Okay. So the cross section of the tube is 300. If a tensile force of 100 kilonewton is applied, find the displacement at the lower end of the rod. The elastic modulus for steel and aluminum are given. If you take the rod, the rod has a length of 300. It is under a force, axial load, 100 kilonewton. So for the rod will be elongated. How do you calculate it? PL over AA, force newtons, length, that is the area, and that is in gigapascals, the elastic modulus. The result is 0.477 10 to the minus 3 meters. So this rod will get elongated. What about the pink tube? The pink tube is compression. So this force is transferred with the help of this piece to the tube, and the tube is under compression, same force, but it is negative because it's compression. So again, we put the tube's, let's say, length, area, and the tube is aluminum, so it has a different E value. The calculation shows me that it will be shorter by 0.952 10 to the minus 3 meter. So what about this point? The question is this displacement at the lower end of the rod. So this point will move downwards. And how do I calculate it? It will be moving downwards first because the rod is elongated, and second because the tube is getting shorter. So the displacement will be this value plus this value, and altogether 1.429 millimeter is the result. Well, we have to talk about stress concentration. So if you have a plate like this, you apply forces, and when you cut here, you can find sigma very easily, so that you take P and divide it by the area. If you have, for example, a hole in this plate, now this section will get smaller, so it will have two parts, the upper and lower parts. You can calculate the sigma, again, P over the new area, A prime. A prime is lower than this A. Okay, so in this region, you calculate a sigma average. And in this region, again, if we do such a calculation, you can calculate an average value, assuming that the stress distribution is uniform. But is it uniform? That is the question. No, we will have a stress concentration, and in these areas, we will have significantly greater stresses than the surrounding areas. Where does the stress concentrations occur? They occur when changes in the geometry of a component is present, and these will influence the flow of the stress. Well, like in our case, you see we have a hole. You see the flow of stress is influenced, and in reality, the actual stress distribution is at these corners, not the average stress. We will have a higher stress than the surrounding area. We will have our sigma max. So the ratio of sigma max to the average stress is called K. K is the stress concentration factor. So when you have a mechanical design with holes, with notches, with grooves, and that type of sectional changes, then you have to consider the stress concentration. The calculation of an average stress is not correct. To do it, well, we have, let's say, graphical aids in order to find the stress concentration. Here you have two simple examples for hole, for fillet, and so in engineering handbooks, you will find hundreds of such graphs for finding the stress concentration. If you're in the elastic area and you know, for example, W, you know this thickness, you know the R value, this is the radius of the hole. So calculating R over W, well, gives you the stress concentration. For example, R over W, R is the radius, W is the width. For example, it's 0.2, so you find out that your K for this hole is 2.4. You see, it's not a very low value, so it is 2.5 times higher than the average calculated stress. For fillets, well, the influencing geometry is W, the radius of this fillet, and as you see, the thickness of the smaller section. So you calculate R over H, you calculate W over H, and having these two values, you can find for example, if R over H is 4.4, and you go up for, let's say, for W over H3, and you find that your K value is 1.5. Well, in engineering handbooks, well, you will find such stress concentration graphs. Let's make a simple problem. We have a steel bar. The dimensions are given. Here it's 20, and here it's 40. So the force P is given or asked. It is asked. We have to determine the largest axial force which is possible if my allowed stress is 150 megapascal. So let's calculate, well, the stress in this section. You have P divided by 20 times the thickness is 10. 10 is the sigma in region 1. But about the sigma in region 2, it is P over 40 times 10. That is in region 2. But these are sections where we are far away from the cross-sectional changes. We have here a cross-sectional change. We have here a fillet. We must calculate the stress concentration with the help of the graphs we have already shown. Okay, let's take this area and calculate the normal stress at the smallest section. As I told, it is P over 20 times 10. This value is 0.005 P Newton per millimeter squared. This is my average. Now I have to find a K value, and this K value will tell me how much the sigma max over here is higher than this average value. I need such a graph. I have R is 10, H is this 20. You see, this is H and this is R. R over H is 0.5. And Using this graph, I have to determine W over H. W is the higher width. It is 40 divided by 20. It is how much? 2. So let's start here. Here I start with 0.5 and go up to this curve. This curve looks like this, and we are here. And when I go to the left, it's approximately 1.4. So this is the average. This average should be multiplied with the stress concentration factor. 1.4 times the average. This value should not exceed 115. That's the allowed stress. And using these numerical values, I find that P equals 1643 kilonewton is the largest axial force which can be applied to this member without failure, without exceeding the allowed stress, I should say. Okay, that's the end of this video. In this video, we have discussed the axial loading, how stresses, elongations, or shortenings can be calculated. We have solved some problem, and at the end, we have discussed the effect of local stress concentrations. Thank you for listening.